let's say that we are given a 14-inch rod that is connected to a circular plate or a disc. So the rod is 14 inches in length and the disc is 8 inches in diameter, and the weight of the rod is equal to 10 pounds. The weight of the disc, or the flat circular plate, is 6 pounds. And I wish to find inertia, mass moment of inertia about the mass center of the composite body, and about point O and about point C. If this was point O and this was point C and this was my mass center G. All right, looks like we're going to be using some parallel axis theorem because we've got composite bodies. And the first thing I need if I'm going to find the mass moment of inertia about the center is where is the center. Okay, so I'm going to call that Z bar. So Z bar is equal to sum of each individual mass, that's a lowercase m, little m I, Z bar I divided by the sum of the mass. Okay, but I have weight, I don't have mass. Oh no, that's okay. Mass is equal to weight divided by gravity. Weight divided by gravity. So the mass of my rod is going to be 10 pounds divided by 32.2 feet per second squared, and that is going to give us 0.310 pounds second squared per foot, or a slug. And then mass of my disc is going to be 6 pounds divided by 32.2 feet per second squared, which will be 0.186 pound second squared per foot. Now I have mass. Now I can find Z bar. So Z bar is equal to 0.310 times, let's see, that's the rod, so I need 8 inches plus 14 inches divided by 2. So that goes all the way up the disc and then halfway up the rod, and then plus the disc, 0.186 pounds second squared per foot. I know I'm being jicky with units, I apologize. And then halfway up the disc, which is 4 inches, divided by the total mass, 3.10 plus 0.186 pounds second squared per foot. And that gives me a mass center for the composite body of 10.875 inches, which is going to equal to 0.90625 feet. I'm wanting everything to be pounds and feet because my mass, I've gotten pounds second squared feet, so then that gets me in all the same length and force units. We do not have pounds mass in this class, we only have pounds force. So this is equal to 0.90625 feet. All right. So now that I know that, I can find my composite centroidal moment, mass moment of inertia, which is going to be the sum of each individual mass moment of inertia plus their mass d squared. Okay, so let's do rod and disc, where rod is in red, 1, and disc is in green, 2, because Christmas colors are fun. So the rod has a centroidal mass moment of inertia of 1/12 mass times the length, and that is in feet squared, plus the mass times the distance I want to travel. Okay, so measuring from the bottom, I need to move the entire disc plus halfway up the rod, and then I'm going to subtract that centroidal distance measured from the bottom squared. I'm going to add to this the disc. The disc has a centroidal mass moment of inertia of 1/2 the mass times its radius squared plus the mass, and then the distance I want to travel. So that's going to be the radius minus that location for the composite centroid squared. Solving my math, I have the centroidal mass moment of inertia is 0.14327 pound-feet second squared. Now that I have this one, I can use parallel axis theorem to move to a line through O and a line through C. IO is equal to that centroidal mass moment of inertia plus the total mass, and then the distance I want to travel, which would be from the center to the top, 9271 squared, which is equal to 0.5696 pound-feet second squared. Mass moment of inertia about an axis that passes through C. Everything is the same except the distance I want to travel. Because now I'm going from the center to the bottom of my shape. 90625 squared. That's going to be a slightly smaller 5506 pound-feet second squared.